Today we're going to look at inverse functions, and part of the definition of inverse functions has to do with one-to-one functions, which is a definition from one of our previous lectures. So quickly, let's just revisit what it means to be a one-to-one function so that we can then think about that in the context of inverse functions. A one-to-one function is a function where each output value, so each y value, corresponds to exactly one input value. So for any y value that we pick, if we think about where that function has the output value, we see that it only intersects the curve once, which means there's only one corresponding input value for this output value. An example of something not being one-to-one, one of our most fundamental examples is the x squared function, the parabola. Because notice for any positive x value or y value that I pick, we see it intersects the function in two locations, which means for a fixed output value right here, there is more than one corresponding input value. So this would be a not one-to-one. So this is the definition we want to keep hold of as we look at inverse functions. So when we talk about whether a function f of x has an inverse function, we first have to know if the original function is one-to-one. Because only one-to-one functions have inverse functions. Now let's take a brief look at the notation for inverse functions. To represent an inverse function, you first name the function in question, in our case the function f, and then to indicate that you're at the inverse is you put a superscript -1. Now in this case, when it's written in function notation f to the -1 of x, always in this case the -1 is not an exponent, it's just a notation, where it represents the inverse function of f. So reading this from left to right, I would say this is f inverse of x. So based on our original function f of x, we can define the inverse function to be f inverse of x. Now these two functions, f and f inverse, have these properties. First, we have that if you compose the function and its inverse, so notice the inside function, this composition is the inverse, composed inside the original function. Originally, we inputted x to the inverse function, and then through function composition, f inverse of x is the input to the function f. Well, what you get back from this whole procedure is when you compose inverse functions, you get the original input back as a result. So we inputted x to this expression, and we got x back as our answer for all x that are in the domain of the inverse function. And we also know that it's true that if you compose the inverse functions in the reverse order, so now we input x into the function f of x, that result is the input to f inverse. This composition will yield just x as the result for all x in the domain of f. And one thing we want to keep in mind is that not all functions are guaranteed to have an inverse, specifically because not all functions are one-to-one. Now here we've got a table where our function f of x is defined where at these x values, we've got these corresponding output values, and we're asked to find the inverse function on this blank table. So for x values here, we've got f inverse of x. And to find the values in the table, there is a pattern that we're going to describe after this, but first let's come up with why the pattern works. We know if functions are inverses, then f of something, when you form this composition on the left, all you should get back is your original input value. And we know how for certain x values, the function f of x behaves. So for instance, let's pick our first x value. In this case, let's look at x is 0. So if we form this composition, f inverse of f of the input 0, we know should give us 0 back as the result. So we know the output of the inverse function is 0 when the input is this expression. So let's fill this in the table. The output of f inverse is 0 when the input is whatever this is. But we've got a table of values for f, so let's look at x equals 0, our input. Do we see the corresponding output as -1? So this would really simplify to be f of 0 is, more simply stated, -1. So in order for this inverse function composition relationship to work, in this case, when the output of f inverse is 0, the input would have to be -1. See if you can recognize there is a pattern here. See if you can see what happened in the pattern of input and output values between the original function and its inverse. From this first example, it looks like they just switched input and output values. That is the pattern. Let's see how that holds again. So we are going to repeat the process. We know that if we're finding the inverse function, by definition, this relationship must be upheld. So we are just going to pick new values. So for instance, we pick an input value, and we know whatever the input value to this expression is should be the output value. So picking the new input value 1, we would get f inverse of f of 1. If they're really inverse functions, then when you compose the inverse with the original, you're forced to give back the original input. So this tells us when the function f inverse takes on this as the input, the output is 1. But what is f of 1 really? That can be simplified based on our table of values. When x is 1, f of 1 is 3. So this really simplifies to when f inverse takes on the input 3, the output must be 1. And again, we see the pattern that to find the inverse function values, you just reverse the input and output of the corresponding function value. So let's complete the table. Again, the only thing we know about inverse functions right now is when you compose them with the original, you've got to get back your input. So now let's pick the input 2. We just worked with 0 and 1. So now this takes on the value 2, and this is forced by composition of inverse functions to give back 2 as a result. So we know the output of f inverse is 2 when the input f of 2 is 4, because f of 2 is just a stand-in for 4. Okay. Now, why don't you take a moment to attempt the remaining parts of our table. So we know the only thing we can work with is this inverse relationship. And we're just going through the given x values for the function f of x. So we've done 0, 1, 2. We have it remaining to do 4 and 7. So whenever the input takes on the value 4, this composition must give as a result 4. So based on this, why don't you pause the video and fill in the remaining 2 parts of the table, unpause to check your work. So here we know when the output is 4, the input was whatever f of 4 is, but looking, that's really -2. So this expression must hold. So for the input -2, the output better be 4. And repeating this idea for our final value, when the input is now 7, this resulting composition must be 7. So that tells us the output of f inverse is 7 when the input is f of 7, which f of 7 is 5. And that completes our table. So given a table of original function values, you can always form a table of values for the inverse. And what you do is everything that was the input of the original expression becomes the output of the inverse. And everything that was the output of the original expression becomes the input of the inverse. And notice between these, the ordering is matched. So 0 is matched with -1, -1 is matched with 0. 2 is matched with 4, 4 is matched with 2. And this is an important idea, that in order to find an inverse function, if there is one, all you have to do is switch the domain and the range. So for instance, if we have our function f of x, whose domain is A, and whose range is B, then f inverse is the inverse function of f of x if it exists. We can know what is the domain of f inverse The domain of f inverse is the range of the original. The range of f inverse is the domain of the original. So in this case, our range was called B. That becomes the domain of f inverse. The range of f inverse becomes the domain of the original, which is A. So between functions and their inverses, the domains and ranges switch. And that's the key idea here for an inverse function. And that's what we saw in this table. The inputs of the original became the outputs of the inverse. The outputs of the original became the input of the inverse. Now in this next example, we're going to use our definition of inverse functions to verify if two given functions are inverses. The key thing that you'll want to remember throughout our entire course is that the idea of inverse functions is that if two functions are inverses of each other, then you can compose the functions, as we discussed in an earlier section, and the result of the composition is the initial input to the inside function. And the important thing about inverse functions is this can happen in any direction. So we can compose the original with the inverse, or we can compose the inverse with the original and still get the initial result back. So we input x into the original expression, input that into the function f, and the overall result is x. Similar here. So if we're given two functions and we're asked to verify if they're inverses, what that means is we need to form the compositions in both directions. And we'll know they're inverses if, after simplification, both expressions simplify to think what would go here based on our definition. X, because that was the initial input. So if this happens, then we know f and g are inverses. If it's not, then they are not inverses. So that's kind of our outline for any type of verification if things are inverses. Compose them in both directions and see if you get only x back as a result. So let's begin. We're going to compose f of x with the function g of x. So our inside function is g of x, which is 1 over x, then subtract 2. But what does the function f of x do? F of x takes an input, and it says 1 divided by that input plus 2 in the denominator. So what's going to happen is when we compose f of g of x, it's going to take the input and then add 2 to it. So we've got our g of x as our input, but g of x can be written in a different way. It's 1 over... That's our g of x. And what are we doing? We're adding 2. So as we simplify this, we see that the parentheses here aren't separating anything. We could drop them without any loss of meaning. So we've got a minus 2 and a plus 2. These would cancel each other out. And we get 1 over x. Now this simplifies to x. You can memorize that 1 divided by 1 over something is just that something. Or you could see this through the division of fractions. See 1 as 1 over 1, because 1 over 1 is 1. Then by dividing fractions, you keep the first fraction, you change the sign to multiplication, and you flip the second fraction. 1 times x is x, 1 times 1 is 1, and we just get x back as a result. So that's why this simplifies to 1. So that's great. We've seen the first part of this. Now we need to check if the same is true when we compose g with f of x. So now we form this composition. We know the function g takes whatever input it gets, and it says we're going to take that input, 1 over that input, and then subtract 2 separately. So here our input is now f of x. So the structure would be 1 over whatever f of x is, that we then subtract 2. That's the structure of the function g. And then we're going to simplify. We know f of x is 1 over x plus 2. Minus 2. Now this term here simplifies by our keep it, change it, flip it idea to just x plus 2, because you would have the first fraction is the same as 1 over 1, because 1 is 1 over 1. Change the sign, flip the second fraction. Fraction multiplication is top times top, bottom times bottom. Okay, so this first term simplifies to just x plus 2. That we were subtracting 2 from. The subtracting and adding 2's cancel, and we just get x back as a result. So since in both directions of the composition we got our input x back, our conclusion is that f and g are inverses of each other. Now for the next example, it's the same instructions, show whether these are inverses of each other or not. This would be a time that I would ask that you pause the video, work out this problem on your own, make your conclusion, and then unpause to check your work. So take a moment, pause the video now, and then unpause to check your work. So as we start, let's compose f with g of x, or you could start with g of f of x. The order doesn't matter, so long as you do both in each direction. The function f of x takes whatever input it gets and cubes it. So in this case, we're just going to take our input g of x and cube it. But g of x could be expressed as 1/3 x. That's what we're cubing. And here we'll want to remember the algebraic understanding of exponents, where if you've got something times something to an exponent, the exponent goes to each term across multiplication. So the cube goes to the 1/3 and also to the x. So this would be 1/3 cubed times x cubed. Now 1/3 cubed is the same as 1/27 x cubed. So here we see that these are not inverses because this is not x. So we don't even have to check the other direction. If one of them fails, that's enough for the whole thing to fail. So we would say, so f of x and g of x are not inverse functions of each other. So how do we find f inverse if we're just given the equation for f? And we can do this with a few simple steps. Step 1 would be to switch the input and output variables, which is commonly known as switching the x and y. Once you've done that, step 2 would be to solve the equation for the output variable, which is commonly known as solving to get y equals by itself. Whenever you get this expression, this is your f inverse of x, whatever it's equal to. So let's do this with our first example. Here we're given the function f of x, and we're asked to find the inverse function. Now first we know that this is a straight line. Looks something like this. And straight lines are 1-to-1, so we know that this has an inverse function. So we know that f of x has an inverse function. The way we would find it as step 1 is we would switch the output and input variables. So just for easier writing, we can change the name from the function f of x. Let's just call it y, so it'll be easier to look at. So step 1 is we are going to switch the x and y variables. So we now have the expression x equals y plus 6. Step 2 is we're going to solve for y in that expression. So to solve for y in this case, it's as simple as subtracting 6 from both sides. And we get that y is x minus 6, but y is really the stand-in for our new inverse function that we found, so we would call this f inverse of x. And the reason we call it f inverse is this tells us the inverse function of f, which is what we were given originally. Continuing with our next example, the instructions are still the same to find the inverse function of the function given. In this case, g of x is 3 divided by x minus 5. So this function takes the input x, and then it sets up the fraction 3 divided by the input value, where the input value is subtracted by 5. So for this example, we're going to find the inverse function g inverse of x. With our two steps, we're going to switch the input and output variable. So let's just replace g of x here with y. It's easier to write the output variable. Switch x and y, and then isolate y equals. And for this one, why don't you pause the video now, attempt the problem on your own, and when you're ready, unpause to check your work. So here with step 1, we're going to switch x and y. So we're going to get the expression x equals 3 divided by y minus 5. Now step 2 is going to be to solve for y equals. The first thing that we're going to do to solve for y equals is we need to get y out of the denominator. So we've got our expression here, and I'm going to multiply both sides by y minus 5. What's done to one side of the equation must be done to the other. And that's going to cancel it from the denominator on this side. And we'll get the expression y minus 5 times x equals 3. Now our goal is to get y by itself, so we gradually move things that are farthest away from it on its side first. That would mean we're going to divide both sides by x. The x's cancel each other on the left, and we're left with y minus 5 equals 3 over x. That should have been a 5. To solve for y, we just need to add 5 to both sides. The 5's cancel, and we get y equals 3 over x plus 5. Now this y represents our g inverse that we were looking for, so we're just going to relabel that as g inverse of x is 3 over x plus 5. So that's our answer. And keep in mind there's a great way that you can check your work. If you wanted to verify if your answer was correct, then remember you could take g, compose it with your g inverse that you found, and if you get x back, and if you do the reverse, if you take the g inverse, compose it with g of x, and you get x back as a result, then you know that they are inverses and you got the correct answer. So you can always check your work via this method. In our next example, it's the same as before. We're being asked to find h inverse of x if h of x is 2x divided by negative x plus 3. We've seen the procedure before. The only thing that changes is you still switch the x and y and you solve for y. The only thing that makes each of these problems different is the algebra steps it takes to solve for y. But the structure of the argument is still the same. So we are going to switch x and y, so I'm going to replace h of x with y. And again, I think this is a great opportunity for you to attempt the problem on your own. So pause the video now, attempt it, and then when you're ready to check your work or get a hint, you can unpause and see the solution discussed. So here with our step 1, we are going to switch x and y, and that gives us x equals, now since there's two x's, we've got to give a y to both of those locations, so 2y divided by negative y plus 3. So everywhere there was an x in the original, there's now a y, and then we switch the x with the y there. So step 2 means we need to start solving. And in order to get a single y, we first got to get rid of this fraction, because we're not going to be able to get down to a single y until we get rid of the fraction. So let's multiply both sides by this negative y plus 3. That clears it on the right side. Notice how I'm keeping it in parentheses to show that we're going to distribute. Okay, so then we get negative y plus 3 times x is equal to 2y. Now the goal is whenever you've got multiple y's, you would like to get all the y's to one side, but notice I can't move this y until I get rid of the multiplication. So I'm going to distribute the x because it's getting multiplied across the sum. So the left side simplifies to negative xy plus 3x equals 2y. Now if we're ever going to get a single y, we would need to get all the y terms to one side. So let's add a xy to both sides. That cancels that side, and we would get 3x equals 2y plus xy. I'm going to continue my work up here. Okay, and notice you've got a y, the same term, on both sides of this sum. Whenever you have a same term on each side, you can actually factor out the common value. So if we factor out a y from this term, we'd just be left with 2. Factoring out a y from xy would just leave us with x. And notice now, through factoring this common term, we now have a single y because we factored it out. So to solve for y, we would just need to divide both sides by 2 plus x. And we would get y is 3x divided by 2 plus x. Now, of course, y is our stand-in for what we solve for, our h of x inverse. So we'd say h inverse of x is 3x over 2x, or 2 plus x. So we've just seen how to look at inverse functions related to their graphs, we've seen how to look at inverse functions related first to tables and then to equations, and we know functions can be represented by tables, graphs, and equations. So now let's take a look at what inverse functions look like when graphed with the original. Here we've got our function f of x and its inverse, f prime of x, is graphed here. Now, when you graph a function and its inverse on the same axis, there is a symmetry to them, and it comes down to the idea that to find the inverse function, you would just switch the input and output values. What that looks like graphically is just reflecting the original expression across this y equals x axis. So notice our f of x, if we could imagine folding our paper along this dotted line, it would line up perfectly with our f inverse. And let's look at a point here. For the original function, at x equals 2, do you see the output is 4? So if we've got x, f of x, at 2, the output is 4. Now, if what we've learned about inverse function holds, then for f inverse of x, it should switch the input and output values. So if this holds, then we should get the pair 4, 2, because the input and output values are switched for the inverse. Let's see if this holds true. So we should go over 4 in the x direction and up 2 in the y direction. So because we've got this switching of the input and output pairs, that's essentially the same thing as reflecting across this line, y equals x. So in our next example, we've been given a graph of the function f of x. We notice it's a straight line with negative slope, its y-intercept is at 3, and we're asked to sketch a graph of f inverse of x. Now you can do this in a lot of ways. If you're very good at visualizing, you could imagine the line y equals x and reflect it through. Or you could pick a few clear points and then remember that inverse functions switch the input-output pair. So for instance, f of x very clearly has a point at 0, 3. Another clear point is 2, 0. So I could quickly from the graph make this table of values 0, 3, 2, 0. And then from this, I know that an inverse function switches the relationship between the input and output values. So if the original function had an input of 0, the inverse function has an output of 0. If the original function had a corresponding input of 3, the inverse function has a corresponding input of 3. So notice the inputs become the outputs become the inputs. And that holds here for 2 and 0. Now I could graph these 2 points, and since its inverse would also be a straight line, from 2 points that would be enough to graph it, because the inverse of a straight line is another straight line in this case. So let's graph f inverse here in this color. So we'd go over 3 and go up 0, and we'd be at x equals 0 and we'd go up 2. So we've sketched a graph of f inverse above by picking a few key points and remembering the inverse switches the input and output pairs. Now here we're asked to find the original function value at 2. We do that by reading the graph, so we'd go over 2 and see where that crosses the graph, and it crosses at 0. So we know when the input is 2 for the original function, the output is 0. Now for the next question they said find f inverse at 0. So for our graph of f inverse, we would go to x equals 0, and then see where that intersects the f inverse line, and it does so here at 2. So f inverse of 2 is 0. Do you notice any pattern between these two values that we found? Notice that since we've got the function and its inverse, oh, and I wrote this wrong, sorry about that. Now that works. So at 0, it's up at height 2. Notice the input of the original became the output of the inverse. The output of the original became the input of the inverse. And this is a pattern that we've seen before for original and inverse functions. Find the domain and range of the original. So the domain, which you can just shortcut with D, range. For a straight line like this, the domain, it can take on all possible x values, because as it continues out forever and ever in both directions, it's going to eventually go through all x values. So we would say the domain is negative infinity to infinity, and the range is similarly also negative infinity to infinity, because imagine it going off in this direction forever, it's going to eventually hit all y values. Now the domain and range of f inverse, we know it just switches the domain and range of the original. So in this case, the domain of the original is this, so that would be the range of the inverse. Now in this case, they happen to be the same thing, so you're not going to see the pattern really, but it's still going on here. The range of the original becomes the domain of the inverse. So as we close, remember the key thing to remember about inverse functions is first, a function's only going to have an inverse if it's 1-to-1. Additionally, when you compose inverse functions, you get the original input back as a result. And given a function written as an equation, how do you find the inverse? You, step 1, switch the x and y. Step 2, algebraically solve to isolate y.